So I guess the plan today is sort of threefold. What I want to do is give some motivation for derived categories, um, and explain, where one or why one might want the sort of technology to exist. And the second part is going to be to uh, actually develop some basic facts about them. Um, and I say develop, but it's going to be very, very fast and loose, just so we can actually get some meaningful conclusion of this talk in a reasonable time. And the last part is what I want to do is apply some of this information to study various cohomology theories um, that arise when one does sheaves. Um, and I think this last part is kind of the most important part, in that it kind of will give us a glimpse of some aspects of uh, motivic behavior, and also highlight why one might think about um, uh, like a hypothetical category of motives, or sheaves valued in motives, for example. Okay, so yeah, let's first start by I don't know, doing a quick review of some classical homological algebra from like the 1930s or so. So let's take R to be just some commutative ring, um, and let's just take M to be an R module. Then it's I mean, what you usually do in the intro to algebra class is something like looking at the functors um, that of the form M tensor R blank. And so this takes you from R modules to R modules. So it's a functor between two abelian categories, but in general, it's not exact. So it's not usually exact. I.e., it doesn't usually send short exact sequences to short exact sequences. So what can we say? Well, it is what's called right exact. So if we have a sequence, a short exact sequence n1, n2, n3, then we'll get a short exact or not, sorry, we'll get an exact sequence um, of the form. So this is what's called right exact. The key part that's missing here is that we don't have exactness at this last place. This map this last map or this first map might not be injective. And so this is kind of a pain, partly because exact functors are nice and we use them to do computations. We can often do things like induction with them, and all sorts of clever arguments often come down to some version of exactness. And so what do we do about this failure of exactness? So how do we save ourselves? And I don't know the history too well. Uh, uh, but my understanding is that, like, 1930s, they developed like the first derived functors, at least in this context, maybe for like abelian groups or something instead. But like very, very early, these were developed, and the idea is that we can measure the failure of exactness using these derived functors. And so the solution, at least in this particular case, is to uh, use derived functors which are called Tor. Um, and the key thing is that instead of getting just a right exact sequence where we don't have exactness in the first step, we could extend this to a long exact sequence where it's exact. And the size of these tors tell you like how far you are from actually being exact. So we in this case we get a long exact sequence. And I think I use slightly different uh, cohomological numberings than most, but I prefer to think of Tor as being in minus degrees. Um, oh, I did something wrong. Oh, this should be minus two. Okay, so I don't have enough space to put the whole thing, but the next part is just the normal exact sequence. So this corrects it and gives you a precise thing. And in a lot of cases, for instance, if you work with like abelian groups or something, Tor will end very fast. I mean, for abelian groups, the Tor the minus two Tor will vanish, or second Tor, or whatever you want to call it. And so this kind of gives some correction, but I think there's a lot of mysteries in these, and just immediately. Um, so one is it doesn't really feel like it's quite the right thing. You are creating a bunch of functors instead of to address one single functor, and it also seems to yeah, I don't know. I think it's just kind of a mysterious thing. Like this connecting morphism here is quite odd. It isn't clear how one might do this in more general.
Actually, it's something. So this is called a delta functor. You shouldn't view this as a bunch of functors. You should view all the tors to be a functor with a delta inside. So it's kind of combined. You do not map from abelian groups to abelian groups, but to from complex of abelian groups.
Yes, we're going to get to the sort of like derived category perspective at least.
Yeah. Okay. Sorry about that.
Yeah. No, but I mean, like, I think it's easy to start coming up with ideas of how you can make a more unified perspective. Um, but so that's kind of the goal is like, how can we give maybe a cleaner description of this, as well as how do we explain, um, yeah, how can we generalize this a little more? So here's another, like, I guess, remark that things that could be desired. And this kind of goes into more general derived functors. So, Um, here's the first thing I want to say. So we have this global sections functor from sheaves on a topological space, say valued in abelian groups, um, to abelian groups, and this functor is left exact. And so it admits right derived functors um, using like injective sheaves, which are always known to exist. And one thing to note is that when X is, I'm just going to say nice, um, this is telling you about the cohomology of of X. So if we look at and plug in the sorry, if we plug in the constant sheaf, we get that this is the same as the singular cohomology of X. So nice is doing a little bit of work, but I mean, I mean, if any manifold, for instance, this would be fine. Or any algebraic variety over like the complex numbers and you look in the analytic topology, this would be fine. And so the takeaway is that in this case, the derived functors are telling you something about cohomology. And this is should kind of be slightly off in your mind because the cohomology is already a shadow of something. It's already a shadow of like the chain complex of singular cochains or something. So this is already indicating that R I gamma is a shadow, I'm gonna say a cohomological shadow of something. And indeed, like, how do we actually compute these derived functors? We take an injective resolution of our uh, constant sheaf, which might be quite hard, but we can, in theory, do it. And then we compute global sections on the injective resolution. But it's not clear, like, why, if you pick two different injective resolutions, the cohomology should match. I mean, these are standard arguments, but like this requires some work, and it's not clear how do you make this like lift this into some statement about chain complexes rather than their cohomologies. So the yeah, so here's the basic idea of like of these derived categories then is, can we cook up a way a category that in some ways behaves like, say, sheaves or abelian groups or R modules or whatever, um, such that if we look at the, say, an injective resolution of um, of like the constant sheaf in this case, injective resolution, that these this is not just a map that has cohomology that matches up, but that this is actually uh,
This should be the
an
other way.
isomorphism. Sorry. Oh, yeah. Sorry. Sorry. Sometimes I just immediately think that I'm already derived, in which case
Ah,
it doesn't matter.
yeah, I
Anyway,
understand. So
such that this is actually an isomorphism. So this is kind of the key thing, is like being able to have an ambient category where we can look at things like injective and projective resolutions, and they look the same as the original objects that we started with. And so that's kind of the goal. Now I've said this all for like just a couple key examples, but I mean hopefully everyone's at least a little familiar with like just right exact, left exact functors, abelian categories, and all that.
Yeah, I have a question. What is this
Yeah.
symbol Z lower bar X?
Oh, this is just the constant sheaf on X.
Oh, okay.
So of course the constant sheaf is um, well, it's if you haven't seen it, there's like an obvious thing that you can define, which is usually wrong for the constant sheaf, in that it's there's a constant pre-sheaf, um, uh, and this is just going to be locally constant functions on U, and then we can sheafify to get the actual constant sheaf. And so it's kind of characterized by this. Well, it's not characterized, but one notable property is all its stocks are isomorphic to just C. So it's a local system with trivial monotrumming. Does that help? Okay. So let's now start talking about derived categories. So well, I shouldn't say it's derived categories. First, I mean the examples that we usually encounter when we're talking about um, doing homological algebra, things like abelian groups, sheaves, modules, etc. These are all these are abelian categories, and so they have things like kernels, co-kernels, images, direct sums, whatever. I mean, they're additive. Um, um, but we need to, like, when we're going to talk about the derived category, um, it doesn't quite, I mean, it doesn't fit into this abelian category picture. It needs some extra information. And so what we want to do is instead look at what are called triangulated categories. So we need these, well, I don't know if need is a strong word, but we're going to introduce triangulated categories as kind of an analog of abelian categories, and these should be thought of as the basic structure of things like the derived category. And it also gives you kind of the tools and formulations you need in order to actually like work with them for the most part. And I guess yeah, anyway, we'll stick purely in the triangulated world for now. I mean, it doesn't really play a role, but yeah, anyway. Okay, so here's a definition or most of one. So let's have C be an additive category. So its Hom spaces are enriched over some ring, and we're going to equip it with an automorphism called the shift. So this is part of the data. And once we have a shift by 1, we can shift by -1 using its inverse, and shift by n by doing shift by 1's n times, and so on. And so along with C, we want a collection of diagrams and I'm going to write them X, Y, Z, X shift by 1, and these are called distinguished triangles. And I'm going to just abbreviate these DT. And these should satisfy a collection of axioms. So we will call C a triangulated category if the following holds. So the first axiom is identity. And this says that if we take the identity morphism, then it should behave sort of like the identity short exact sequence, in that it should be followed by 0, and then I mean, there's only one possible map to 0 and from 0. So this should be a distinguished triangle. We should have rotation. So if we have a distinguished triangle and we rotate it, we should still have one. There should also be we should also be able to complete a morphism into a distinguished triangle. And in fact, we want to be able to do a little more. We want to be able to complete a commutative square into a commutative diagram of distinguished triangles. So if we
Yeah,
have a, yeah,
sorry to interrupt. I think the x1 to y1 there should be negative of this. It is flipped, so it is induced from the map from x to y, right? That map is negative when you shift it.
so so we have a map from X to Y, and we've
Yeah,
shifted it the whole map by one.
yeah, and you take the sign as well, the opposite sign.
No, no.
It's
You do.
already encoded in the functor. So as long as you have a functor, you are fine.
Yeah, this is all encoded in the shift by one functor. I mean, even then, like, I mean, for chain complexes, this is literally just shift the chain complex by one.
And by shifting, you do mean what Crescendo said, which is F maps to minus one
Ah,
power.
yes, yeah.
It's
I mean,
encoded in the functor.
yes,
Okay.
yeah.
Okay.
Yeah.
It's in there. Okay.
Yeah, and I mean, one huge takeaway from studying triangulated categories is that a lot of this is just convenient notation and bookkeeping that can be used to make your life way easier when you want to do homological algebra. So, okay, so if we have a commutative square, um, so x, y, a, and b, this should be this should extend to a commutative diagram of distinguished triangles. So I'm not saying what Z is or what these maps are. Right? It should just exist, nor am I actually giving any version of uniqueness. Um, but this should be able to be done. Although you should sort of, um, yeah, anyway, there's lots of exercises one can give. Um, and there's one last one, which I don't really want to write down, but you can certainly look up, and it's called the octahedral axiom. And so we're going to skip this one. So I work a lot with triangulated categories, and I think I've only used the octahedral axiom like maybe 5 times outside of like studying, homological algebra. So it is certainly important, but it is not something you'll look at and then internalize and get any meaningful information out of in a hour-long talk. So we're going to skip it. So I guess part of this is like what should like what should you think of when you actually think of these triangulated categories? And of course, like you should think of things like chain complexes, and in which case, like what does rotation mean? Well, rotation isn't really saying anything here. It's just this idea that we have uh yeah, I don't know. Rotation doesn't say anything. Identity doesn't really say anything. Uh, completion is like I think the only interesting place here, and this is like the ability to take like a chain cone or something of a chain map. So anyway, let's actually write out an example. Um, and so the first example I want to do is just going to be sort of like what I was, well, more or less what I was just saying. So let's take A to be an abelian category. And then we can look at the category of chain complexes in A. And I guess by chain complex, I always mean cochain complex. If you are topologically minded, my differentials always go up. And what we can then do is define a new category called the homotopy category. So define the homotopy category. It's going to be called K of A. And we're going to define it as follows. It's the objects are the same as chain complexes in A. Objects are chain complexes in A. But the morphisms makes it different than just looking at normal chain complexes. So what we'll do is we look at the quotient by so we're going to look at the quotient of the Hom spaces in the category of chain complexes. And we mod out by morphisms which are homotopic to 0. So maps homotopic to 0. So this should be very analogous to what you might do in topology, for example. And I should maybe briefly specify that in the category of chain complex, the maps are chain maps. So they commute with the differential.
Sorry, in topology, what we do in the homotopy category, the two maps are equivalent if they are homotopic to each other. But here you are doing if a map is null homotopic. So
Yes, so you have this wonderful thing in when you work with additive categories, and that there's a 0.
yeah.
And so saying that two maps
Oh,
are
okay, okay.
homotopic is the
Okay,
same
I
as saying
see.
their difference is homotopic to 0.
I see. I see
Yeah,
actually. Okay.
yeah.
Also, yeah, given an abelian category, how do you build a category of chain complexes?
I mean the objects are chain complexes, and the maps are chain maps.
No, that's fine. But you start with an abelian category, right? So let's say you start
Uh-huh.
with a group. How would you build a chain complex out of it? Like, what's the
No,
process?
they're chain complexes whose entries are objects in the abelian category.
Oh, okay, I
So,
see, I
so
see.
like the example is you should like think the abelian category is like R modules or something,
Okay.
or abelian groups or sheaves or what have you.
I see. I see. Okay, got it.
Okay. Okay. And so I need to specify what the shift functor is. I mean, I want to equip this homotopy category with the structure of a triangulated category. So let's start by specifying the shift. So well, yeah, so the shift is going to be I mean, it's just inherited from chain complexes, but we can write it here. And what it does on objects, when we shift, we have a new chain complex. And so I need to explain what its nth term is, and it's going to be the n plus first term sorry, I keep switching between my notes say. So it should be the n plus 1th term of x. So it's kind of again just convention, and I'm not going to write out what it does to the differential. It just does what it has to do. I mean, it's yeah. And so we now need to explain what the distinguished triangles are. This is the shift functor. So the distinguished triangles. Well, we know that from like well, I didn't say no, but we should think that a lot of this should come from like we have certain distinguished triangles that are going to be of the form A, B, let's say this map is F, and then the cone of F, and there's of course a map from the cone A shift by 1. And so this should be one huge class of examples, but it's not going to be all of them. And so we also need to include all of the things that are isomorphic to things of this form. And by isomorphic, I mean in the homotopy category. So we should also look at things that are isomorphic. So really the key players are distinguished triangles, well, diagrams of this form, such that there exists a commutative diagram such that we have isomorphisms. There's some, thing in the distinguished triangle at the bottom variety. Okay, so I think that wasn't maybe the best explanation, but so the distinguished triangles are going to be diagrams of this form, such that there exists A to B along with a commutative diagram as below. Okay, that's not too bad. I think, I actually, I don't know. I think as with a lot of homological algebra, a lot of this is you benefit a lot from just doing things yourself. And so it's for instance, an exercise which is not at all hard or anything, and possibly useful, is to actually check that this is a triangulated category. A related exercise is to check that this is not an abelian category. I guess I think unless A is semi-simple or something like that. Yeah. You have to be slightly careful with these things, but anyway. Okay. Any questions on this example? Okay. If not, let's try to build up to the derived category. And here's the idea. Well, we still have not solved our problem. We still do not have that every map is actually isomorphic to every map is actually isomorphic to, sorry, every object is isomorphic to like a projective or injective resolution of that object. We still haven't got that part. So what we want to do is to somehow invert the maps that sort of behave like that. So let's just recall, so if we have a morphism f from x to y, this is called a quasi-isomorphism. If it induces a isomorphism on cohomology. And the key thing to note is that in K of A, quasi-isomorphism does not imply isomorphism. And it's kind of like in a silly way in that it's just, there's not always a map that goes in the other direction. So like, how do we get around this? Well, I don't know if it's a stupid trick. There's a useful trick to do, which is just, we can localize at the quasi-isomorphisms. We can just make those maps exist and force them to exist. And so that's what we're going to do. So we can fix this by localizing at quasi-isomorphisms. And if you've seen localization of rings and modules, this is effectively the exact same concept, just with a little bit extra categorical flavor. So, what? Yeah, let's define the derived category. I'm going to note D of A as follows. So the objects again are not changing. The objects here are just chain complexes in A. But the morphisms very much change. And so we want to think of this as being like a fraction or something. And the things we allow in the fraction or in the denominator of the fraction are going to be quasi-isomorphisms. So these are going to be equivalence classes of diagrams that are going to look like this. And we're saying that this map on the left is a quasi-isomorphism. So I haven't yet explained what the relation is. So the relation, so we're going to say that this is, one diagram is equivalent to another if and only if there exists a diagram of this form. So it's going to be well, we have to find a common denominator, right? That's what you would do for equivalence classes in your localization rings, and so you're trying to do the same thing here. And so we need to find something that kind of goes between them all. And so this map should also be a quasi-isomorphism. Okay, not the cleanest diagram, but anyway. And so this gives you some class, but it's kind of not clear now what composition should be. So this is probably the most interesting part and what actually requires some work.
Sorry. For localizing in a category, don't you take the equivalence class by zigzags?
No, it could be showing equivalent to this thing. Roofs are much easier to describe. It is the same in this case.
Okay.
Yeah, I mean, so like, there's some like general calculus about localizing triangulated categories, in which using like roof diagrams or basement diagrams or whatever you want to call the flipped ones can be a little easier. And
this is a roof. This is exactly the roofs.
Yes, yeah, these are roofs. And in these cases, like it's a very formal thing in order to do this localization, and it just depends on what maps you're allowed to or what maps you're localizing. They need to satisfy some properties. Anyway, and that you anyway, yeah. This is the right notion of localization that we want to perform. So the composition is the only part that really is mysterious, and we'll emphasize that it's even more mysterious than it may appear, and it's a little bit. So for a composition, we want to be able to compose a diagram like this, and so we need to be able to construct something. Yeah, let me. So we have a diagram like this, and we need to construct something that kind of sits above it. So we need to find some C making this diagram commute, and such that this left morphism is a quasi-isomorphism. So that, I mean, these are both the existence claims. And the fact is that C always exists. And it's a good exercise to prove it. So the exercise is prove it, and it's I say it's a good exercise because it actually gets your hands dirty on these axioms of triangulated categories. In particular, you're going to use things like completion and rotation in order to construct it. And also I should emphasize that the kind of a crucial role here is the fact these are quasi-isomorphisms. You can't just localize it any morphism if you want. Yeah. Okay.
Once again, can't I just take the pullback of
Well,
A?
the pullback may not exist.
Oh, okay. I see.
Yeah. Okay. So the fact is that, again, we're not going to prove, is that this derived category is also a triangulated category. And it's not too much work. Once you have it for the homotopy category, it's pretty easy to reason why it should also be true for the derived category, and so all that. And so what should the intuition be with this? So we've cooked up a bunch of formal nonsense, and we know that it has this one desirable property, which is that quasi-isomorphisms are actually isomorphisms. So things like injective and projective resolutions are actual isomorphisms in our categories. And so we can actually do things like that. But more generally, like, what intuition should we have about like this triangulated structure, and how does it, tell us something? So the intuition one should have in this context is that distinguished triangles are the correct replacement for short exact sequences. And I mean, and I mean, on the one hand, so I guess this is partly a remark. If we have a short exact sequence, then it that I mean, there exists a connecting morphism such that is a distinguished triangle. So it has at least this property. I mean, if we have a short exact sequence, we get a distinguished triangle, and so that's good. But we kind of want to be, I mean, more general. And it's not more general in that it like is weaker really in exactness. It's more general in that it is better behaved with respect to like things like derived functors. So here's a fact, which is if we have a map called cohomology, I guess I should probably put like an I or something. So we have a cohomology functor, which does does exactly what it just takes a chain complex and spits out its cohomology at the ith step. And the fact is that the cohomology, well, I'm going to say the slogan and then we'll write out precisely what it means. This takes distinguished triangles to long exact sequences. So what do I mean by that? I mean, if we have a distinguished triangle, then we can construct a long exact sequence. and so on. And I mean, like, why should this be? Well, like, you should imagine that, like, this distinguished triangle actually goes on sort of in both directions. Right? We can continue this as before, and rotation says that this gives you distinguished triangles as well. So we could continue this and so on. And we get a sort of thing that looks like a long exact sequence, and we're really just applying cohomology to that as like a functor. I mean, we get some diagram at least. Anyway, so we're applying the ith cohomology to that. Okay, so this is useful because we want a replacement for short exact sequences that allows us to capture this derived notion without having to jump to long exact sequences. And so this looks like a plausible solution. So here's a definition. So a functor f from C to G, this is between triangulated categories. So this is called, well, triangulated. If f takes distinguished triangles to distinguished triangles. Great.
Could you go on? Can you explain one more time what the fact is? So HI is your cohomology factor.
So we have like a functor that takes us from the derived category back to the abelian category, and it's just cohomology. And if we have a distinguished triangle, we can produce this cohomology functor produces a long exact sequence.
Okay.
So I mean, we'll get to an example in like a minute, if that, and that might clear up some confusion, but you should think of like this has enough information in it to because they're like inherently they encode the chain complexes as well. The distinguished triangles incorporate all the information you need in order to actually specify a long exact sequence. And this is like sort of the telling you this exactness behavior. It's telling you, I mean, in the case that this is arising from a short exact sequence, the cohomology, the zeroth cohomology would just spit out the short exact sequence again.
I see. And what is the next line for like X, Y, Z, and then your
I mean, this is like I like you should think of this as being a single HI being applied rather than like all the HIs being simultaneously applied.
Oh, I see.
Right. So it's
Like
HI is
Coupe
being
sequence.
applied to that. I mean, you can also think of it as all the HIs being applied at the same time, but like I don't
Got it. It's like Coupe sequence, that's all. Yeah.
know. Sorry, I didn't catch that.
Coupe sequence in topological safe spaces, maybe, yeah. Like Coupe sequence.
Okay. Okay. So let's get something more down to earth. And uh so let's go back to our example of our modules. So we had this functor. Oh, I guess I was writing. We have this functor, and it wasn't exact, but that's fine for now. And we can apply this on chain complexes to get a functor that I'm just going to denote the same. Between chain complexes. And it's not hard to check that this functor will take things that are null homotopic, two things that are null homotopic. So it induces a functor at the bounded or the homotopy category level. I should say probably bounded homotopy. Yeah, let's just I'm gonna add a B here, and all this is saying is bounded chain complexes. So we don't allow them to go in infinite directions. This is just to prevent possible things of me saying wrong here in a minute. So yeah. Okay. So what we can then do is for each chain complex, or I mean, really, you should think for every for every chain complex, we can find a chain complex uh do I actually want to say this? Yeah, I think this is okay for now. I might need to make an assumption here that anyway, this is fine. So I want to find a chain complex which is quasi-isomorphic to it, such that P is um, a chain complex of projective modules. This might be too strong, so you could also say for like replace this with a chain complex of or free modules, for example, or not free modules, sorry, flat modules. So I think if we have to assume like the ring is perfect or something in order for every this to actually be true on the nose, but anyway. And what I want to do is I want to define a functor, and what it does is it should encapsulate this derived behavior. So it's the left derived functor of the tensor product, and it's going to go from the derived category of R modules to itself, and I mean, how do we define it? Well, it's by this formula. Oh, sorry. We define it by the formula that it should be just the tensor product of the projective resolution. And so this asks, I mean, this opens a lot of questions that I'm not going to answer, but it's very similar to the sort of questions you encounter in usual homological algebra, things like, why is this independent of the resolution? You know, questions of existence about, you know, what I said projective modules, but then also said flat. And anyway, lots of questions, but this is the basic formula. We have a functor. It was not exact, but in the derived category, every object is equivalent to its projective or injective resolution, or if we maybe work with flat things, or if we're working with sheaves, maybe we're working with like flabby sheaves, or whatever, some nice class of objects that functors are exact on, and then we can use that to define our derived functors. And the moral of this story is that when we take the cohomology of this, and maybe for like just something concentrated in degree 0, then this actually is the same as our dwarf from before. So we're actually able to sort of recover this dwarf, but it's encoding it in a way that's like at a chain complex level rather than the cohomology level. So the cohomology is now a shadow of this derived functor. This is like mostly neat language. And so this is a good time to ask for questions. And if not, then we can talk a little bit about sheaves.
My other question is some other examples, maybe.
Yeah, well, I'm going to do another example. So let's go back to sheaves. So we can define the derived global sections functor in the exact same way, although here we should use I mean, this should be something like the global sections of an injective resolution or something.
So what's that symbol that looks like 7?
Uh,
Gamma of what?
the symbol
Yeah.
that's supposed to be an F. I don't know. This is how Pramod draws them, and I don't know. He ingrained this into me like 5 years ago, and I just draw him the same.
Okay, okay, okay.
Yeah, so you can blame him. Okay, but you can define it the same way. You have to find a nice class set in which the functor is actually exact on, in this case, injective, sheaves, and continue as before. And the upshot again, or the moral is in this case, well, if we take the cohomology, we get these derived functors we had before, and this is actually like the same as our singular cohomology. Oh, I shouldn't. Okay, and I'm gonna anyway. It is if you plug in the constant sheaf. So we can actually think of this as kind of like a sheaf enhancement of like some singular cochains or something, but for arbitrary sheaves. And I mean, it doesn't actually match up at the cochain level. It's only something you get to when you pass the cohomology. But like you should think of this as being a way of creating cohomology theories or maybe creating new perspectives on existing ones. And here's a really fun fact, is that we can actually describe this in a different way. So we can actually give a different description of this. Um, this is actually the same as the palms from uh, well, let me specialize, and this doesn't change at all if you do it differently, but my remark afterwards becomes more clear. So if we plug in the constant sheaf here, this is actually the same as the space of homomorphisms from the constant sheaf to itself, but shifted by I. And so a couple of remarks about this is the first is that if you work in the ordinary um, if you work in the ordinary uh, category of chain complexes, this is usually zero, right? The constant sheaf is concentrated in degree zero. If we shift it by anything that's not zero, then we're going to no longer be there and it'll be zero. So the derived category has a lot more interesting comms um, uh, that are just not present. And so the other perspective is that we can actually think of this derived, and we can think of this singular cohomology as being like an endomorphism algebra of the constant sheaf. And what's cool about that is that with the algebra structure, which corresponds to composition, is the cup product. So the cup product then will just correspond to well, we can plug in um, something like this. And if we have a G and an F, we can map this to, well, we need to shift um, G by J and then just compose it with F. So composition is the corresponds with the cup product. So that's kind of neat. Okay. Any questions before we get to the last little part? Okay, so I guess this is part 3, and I'm gonna give a greatly abridged version of maybe what I was originally planning for the sake of time. But the idea is we can discuss how different sheaf theories give rise to different cohomology theories. And so in each of these cases, there'll be some derived category of sheaves, and there'll be some version of things like global sections or maybe these hums. And we can use this to define a cohomology theory. And sometimes like these match up with what we know. Sometimes there's something kind of new and interesting. Um, and so the example that we've been going through so far is what's this is a singular cohomology. And the sheaf theory I fundamentally want to associate this is like maybe we think of uh, like X as a algebraic variety or scheme or whatever stack or maybe over like either C or FP bar or something like this. And so if we look at sheaves uh, on the uh, complex points of X, then this is, and this corresponds with like our theory of singular cohomology. But there's a lot of the other ways we can associate sheaf theories to X. So we also saw in the previous weeks that we can associate things like quasi-coherent sheaves on X, and this gives our coherent cohomology, which we talked a little bit about different ways of computing using things like check cohomology and whatever. But this is very fundamentally different in flavor than the singular cohomology. Some other examples which might be familiar or not is we could look at things like D modules on X. And this is, again, assuming that X is like over C or something. And when we do this, we can recover de Rham cohomology. We could also do things that are maybe a little more exotic, like we can look at sheaves on the infinitesimal site. This is I'm not going to explain all of these, but I'll explain some in some more detail. So infinitesimal site. And this would produce crystalline cohomology. And lastly, in this sort of picture that I am going to paint for now, is we could look at what are called the tall sheaves. I have the it's not a tall A. The tall sheaves. And this would give rise to a tall cohomology. So I mean the actual like how you go about constructing these in all the cases is more or less the same. You want to look at like a derived version of global sections, and all that actually changes is like what ambient derived category of sheaves are you working with. So in the first one, we're working with these like I don't know, sometimes they're called Betty sheaves. Or really this lives in the world of like doing constructible sheaf theory. This latter one is very sort of special and really works in the world of coherent sheaves, which we saw before. And the ones that we haven't really talked about in any amount of detail is these last three. And I'm not going to do the crystalline one because that would require us talking about sites, and I'll only, well, what I'll say is uh maybe I'll say just a few words about Atal sheaves, and we can end it there. Any questions or remarks before I continue?
Yeah,
So
so
go
okay,
ahead.
yeah, go ahead. You go ahead. Then I go ask. Go ahead.
You can go ahead. I don't, yeah, go ahead. Yeah.
Okay, so I was just curious about like some of the examples here. Like I want to see like how you get the Dirac cohomology from the D modules on X. Uh,
Okay. Yeah, I mean, I can maybe D modules is a little better. I can give a more complete definition of that at least. Because I mean, the tall sheaves also require some amount of talking about sites.
oh, okay, okay.
Um,
Go ahead. Yeah,
yeah, I can go over D modules. I mean, the takeaway I want from this is that like, depending on what geometry you extract from your like algebra geometric object, you get a different sheaf theory. And
yeah.
from that sheaf theory, you can produce cohomology. And sometimes those cohomologies are different, or sometimes they're the same. And so, like for example, if you look at over like and if you work over like algebraically closed fields, you often like the um if you work with ordinary sheaves, things are, and like in this risky topology, things are stupid. Like the open sets are too big and it just doesn't work well. And so like the idea with like a tall sheaves, for instance, is it's like a way of recovering properties about singular cohomology for varieties and schemes that are defined over things that aren't like the complex numbers. And it gives you a lot of similar properties. I mean, this is a gross oversimplification, but anyway. So let me talk specifically about D
So I'm
modules.
actually want to ask, what do you mean by D modules on X, giving you that thing? So from what I have known is the algebraic de Rham cohomology is defined by say hypercohomology of the de
Ah,
Rham complex on it.
yeah.
So that's not D modules.
I mean, okay. Let me write out what I wanted to find, and then maybe yeah, well, let's see if there's a problem with that. I mean,
Okay.
but so I mean, uh, what is D modules? So this is the category of modules over the sheaf of algebras. So D of X. I may show this in a sheafy way. Uh, and so D of X is the algebra differential operators. And I'm kind of ignoring some uh, sheafy things, but like I mean, if X is, for instance, affine, this is fine. I think. But yeah, anyway, you can define an algebra. You can look at modules over it, and it's maybe these are like viewed as sheaves, but I mean, it is some abelian category,
Actually,
and
this is
there's
something I was told by my advisor, who was told by Burlington or somebody else, or Dreamfield in um who was in MIT, said we shouldn't really read D modules as modules, category modules over algebra. We should read D modules as a single word, something like a German word. D module doesn't mean actually modules over D, which is algebra, which is not commutative algebra.
I mean, it's appropriate to think of these as modules over a non-commutative
No,
ring.
it's not correct. He corrected me very.
I
Uh,
mean, if
no,
X is
I
affine,
no,
this is
it's not
perfectly fine.
true. No, at least it's not commutative. So it's not
Yes.
something. So it's not something. It's not. It's not even. So for instance, how do you define in this way? How do you define the de Rham cohomology of the line?
Okay, so I want to look at okay, so I want to take the structure sheet
So X
on
is very
X.
simple. It's K.
Yes.
It's
No,
spec of
let me propose what the definition should be, and then we can just discuss you know whether it actually matches up. So this is the structure sheet, and then the claim is that in like we can define the Jerome cohomology of X as in the derived category something like this. And I mean, this in some sense is correct because it's like Riemann Hilbert says that this is equivalent to the singular cohomology that we just did. But I mean, it
very so how do you view OX as an object inside D modules?
I you can apply
Let's maybe
differential operators on polynomials.
maybe let's do a polynomial algebra of single variable, which says X equals to spec KX, right?
Sorry, you want X equal to
A1, yeah, spec
okay.
KX. The very yeah, the very
Yeah.
easy. So D is
So
the
so D of X here is going to be the Weil algebra.
yes,
It's the non-commutative algebra generated by
X in
X
D.
and the derivative in X.
Yes.
And we have our like Leibniz rule.
Mm-hmm.
So in this case, it's like, you know, literally just modules over this algebra. Well, I'm sorry, I shouldn't say it's not literally modules over this algebra. That's still wrong. This is like the global sections of this. Like this is when we plug in all of A1. But for example, like if you plug in X minus 0, then you get like the I mean you get something more complicated. And not really, but like I mean, it's not exactly the same. And so I'm looking at like modules in the like the sense of like what Hartshorne chapter 3 or something, whatever one's on quasi-coherent sheaves, and like modules over this algebra. And so certainly like I mean some information is lost if you just think of it as purely a non-commutative algebra, but like in
No, I mean we haven't seen what the cohomology is now here. So we
yeah,
just
so
write it
so
out. So how do we see it?
yeah, I mean we have to go and come up with a this is also not a great example because there's no interesting cohomology.
Yeah, so but if we can't compute see it, then that's a problem even.
Yeah, I mean, there's nothing to say that like these. I mean, oftentimes it's very hard to compute the cohomology from you know this drive story. We can.
And another thing is this true for singular varieties? I don't think this is quite true
Um,
non-smooth things.
I think I want to say that like when you start with the theory of D modules, at least in this generality, it should be interpreted as like always starting with something smooth. I mean, this is not I mean, obviously this is not like strictly needed. Um, but I think
Well, I
yeah,
possibly think way of how to see this thing. So you have the Euro-Dram, which is the wedge product of the module,
sorry,
which
what are
is
you
the
trying?
wedge product of omega x over k.
You're talking about classical Durham cohomology.
Yes. Here you still
Yes.
have omega x over k, which is called the relative. Uh,
Yes, the dualizing sheet.
no, this is not the dualizing shift. Uh,
Under Riemann Hilbert.
no, it's not the dualizing shift. It's the differential modules over differential of differentials. Yes, so if x is smooth, we can have the de Rham complex. I do believe that this de Rham complex should be the complex. If your definition is correct, then there is a way to link the to give a resolution of OX so that this is harm inside the D module,
Mm-hmm.
possibly.
Uh, Professor Hoffman, did you have something you wanted to add?
Well, I just want to jump in here about the de Rham cohomology. Generally, I mean, you're trying to give a D-module approach to it, which I think is possible. First of all, I assume that you're in characteristic 0 because
Yeah.
characteristic P, you really have to introduce things like crystalline cohomology, which are much more sophisticated. But if you just want to do, if you want to do de Rham cohomology in characteristic 0, the classic definition is you start with the de Rham complex, and you can take the algebraic de Rham complex in the Zariski topology. Now, what you do is you take the hypercohomology of that gadget. Okay? So if you know when you have a complex of sheaves, there's something called hypercohomology, right? And you take the so Grothendieck's definition is you take the hypercohomology of the algebraic de Rham complex. Now, usually you start with X to be at least smooth over K. I mean, now, when you want to define things in singular cases, one really has to get into Deligne's mixed Hodge theory, in which case, you know, you're getting into these logarithmic complexes and so on. This is much more sophisticated. But if you want to just do a smooth variety over a field, the definition Grothendieck gave is you take the hypercohomology of the algebraic de Rham complex. And Grothendieck's theorem is that that's the same thing you get from the analytic space. So this is a non-trivial theorem. So, you know, you have de Rham cohomology of manifolds, just smooth manifolds. If you have a variety over a field of characteristic 0, and you embed that field into the complex numbers, you get an analytic space. And that analytic space has analytic cohomology. And Grothendieck proved that those are isomorphic. This is a non-trivial theorem. It's called the algebraic de Rham theorem. So there is a hypercohomology of that complex. And that is, at least when X is smooth over a field of characteristic 0, that is going to be the same as the thing that comes to you from regarding X as a complex manifold. This is a non-trivial theorem. This is a theorem of Grothendieck.
So the hypercohomology though is the same as the cohomology of the like F lower star.
Well, you're taking F to be the structure
Uh,
map spec K. Is that what you're doing?
Yeah.
Okay, so you're trying to, okay. So I suppose you mean probably RF lower star.
Yeah, sorry, I'm just saying derived. Like, I mean, if
Okay,
we're
all
working
right.
with derived categories, everything's derived.
Yeah, all right, right.
Yeah,
Yes. So if you want to say it that way, fine. F lower star is the derived direct image.
yeah. And this, yeah. So maybe my
Now you can express this in the language of D modules. That's possible.
mhm.
And there are
Yeah. I
ways,
mean,
yeah.
I think the claim should be that. I mean, the algebraic the what do I want to say? My claim is that this is quasi-isomorphic to OX, viewed as a D module.
Oh, I don't know
think
about
so.
that.
I don't
Well,
think so. Meromorphic, no. Analytic case, yes, it's under the Dobar. Yes, it's not for algebraic case.
In the holomorphic case, all right, let's go over the complex numbers. The analytic de Rham complex is quasi-isomorphic to the constant sheaf of complex numbers. That's called the Poincaré lemma.
Mhm.
You see, if you're in an analytic situation, so this is a complex manifold now, then if you take the complex of holomorphic differential forms, that complex is quasi-isomorphic to the constant sheaf of complex numbers. That's called the Poincaré lemma, the holomorphic Poincaré lemma. So you're not getting OX, you're getting the constant sheaf of complex numbers.
Yeah, I guess like so under like Riemann Hilbert though, these should be the same.
Well, now wait. So Riemann Hilbert has to do with modules with connection. Now it's true that OX has an exterior D operator. Okay.
Yeah.
Now you're right. Regarding OX with the exterior D operator is tantamount to considering OX as a D module.
Yes.
Okay, yes. So regarding OX in the category of D modules, then that's essentially the same thing. Now, now again, you have to be very careful here with which topology you're in. In the Zariski topology, the thing is that the Zariski topology is really too core. See, de Rham cohomology sees topology, and you can't see topology in the Zariski site. You see that, so it's kind of a little miracle that the de Rham cohomology, which you can calculate in the Zariski topology, really does see something analytic. It sees the analytic cohomology. But that's a deep result. That's not a trivial fact.
Sure.
In any case, thank you, Colton. I have to go now.
Yeah.
I sent you all a little fun reading. You were asking about the history about some of these things, and I found some articles
Oh,
about
perfect.
this history of algebraic, homological algebra, et cetera, et cetera, et cetera. But I have to go now. So thank you. Bye-bye.
Yeah. Okay. Yeah. I mean, I think that's a good place to stop. I don't want to have this drag on too long, but yeah, I mean, I guess the upshot modular details and problems and whatever is that like sheet theories produce interesting cohomology theories. Sometimes these end up identifying, but this can be a useful way of looking at this sort of thing. So anyway.
All right. Thank you, Colton.
Mhm.